Here's the solution to homework set number 1 for ECE 321, Analog Electronics. Now in this homework set, we're building the last part of a multi-stage amplifier, and maybe the last two, an amplifier like a preamp, along with a push-pull. So let's pick your favorite problem. Problem 2 is when we start into the assignment. Problem 2 looks at design an amplifier. 2a, build an amplifier with a gain of 6. Well, that is a non-inverting amplifier where the gain is 1 plus the ratio, 1 plus R1 over R2. So for a gain of 6, I want a 5 to 1 ratio. Pick this 5 to 1. Anything bigger than 100, less than 10 meg. So 1K, 5K works. Problem B is build a circuit with a gain of minus 6. That's the inverting amplifier. There the gain is minus R1 over R2. So for a gain of 6, pick a 6 to 1 ratio, 6K, 1K. Problem 3, build a circuit where the gain is 12 minus 6x. To do that, I rewrite that as 6 times 2 minus x. This amplifier has a gain of R1 over R2 times A minus B, where this is A, there's B, there's R1, R2. So matching terms, R1 over R2 is 6, pick this to be 6 to 1. 2 is A is 2 volts, and B is X, so there's my input. This gives you 6 times 2 minus X, or 12 minus 6X. That's problem 2. Problem 3 is a mixer. Build a circuit with a gain of 3A plus 7B plus 2C. A couple ways to do that. One way is to add a dummy variable X. That's the weighted average of 3A, 7B, and 2C. Adding up all these numbers gives you 12. So if I divide by 12, that's the weighted average. That's this circuit right here. The reason for the 12 is if everybody's 5 volts, X will be 5 volts. So I need to set it up so that, if A is 1, B is 1, C is 1, X is 1, A is 5, B is 5, C is 5, X is 5. That gives you the 12. To clear the 12, I multiply by 12. So add an amplifier with a gain of 12. This is a non-inverting amplifier. The gain is 1 plus the ratio. So a 11 to 1 ratio gives you a gain of 12. And that gives you Y is 12X, or Y is 3A plus 7B plus 2C. One solution. That's a mixer. So you can mix Katy Perry, Iron Butterfly, Grateful Dead together, and with these weightings, and hear what it all sounds like. Problem 4, now we get into push-pull amplifiers. To design a circuit where Y equals X, so here's Y, here's X. Subject to X is only capable of 10 milliamps, Y is capable of driving 200 milliamps, like a 25 ohm speaker. That'd be this guy. This is your NPN on the high side. Here's your PNP on the low side. Take the collector, tie it to minus 10 volts, collector, tie it to plus 10 volts. The emitters get shorted together, the bases get shorted together. Base goes to the op amp, the emitter goes to your load, 28 ohms. And for an op amp, use an op amp so that V plus equals V minus. Here's X. So here's also X. This gives you Y equals X, gain of 1. But what that does for you is I have a high input impedance driving a low impedance load, like an 8 ohm speaker, or in this case 28 ohm speaker. That's a push-pull. If I simulate this in Circuit Lab, I'll do a 1 kilohertz sine wave simulated for 3 cycles. This right here is X. It's also equal to Y, showing that X equals Y. The orange line, just for fun, is V3, the voltage at the base. What happens is over here I'm pushing, the NPN is on, VUSH. Over here I'm pulling. The PNP is turned on, and right here, that's when I go from, I need 1.4 volts to turn on the NPN, because the transistors I used are Darlington pair. 0.7 volts across each diode gives you 1.4 volt drop when it goes plus. And on the negative side, it's got to go to minus 1.4 volts to get the PNPs to turn on. Again, the voltage to base you don't really care. What I really care about is the output. Output equals input. Sine wave in gives you sine wave out. There's no crossover distortion at the zero crossing. Should work. And hardware. There's a couple different circuits for hardware. The first one is assuming you don't have access to a negative power supply. Design a power amplifier capable of driving an 8-ohm speaker. Here's our on-air promotion. Pepsi, breakfast of college students. Okay, carry on. Here the idea is take the input relative to circuit ground, go +3, 0, -0.3 volts. When I'm at +0.3, 2.5 plus 0.3 gives you 2.8 volts. What happens is this is 2.8, V plus equals V minus, this is 2.8. 2.8 to 2.5 is 0.3 volts. Across 1K gives you 0.3 milliamps going down. That 0.3 milliamps goes through here. 0.3 milliamps times 3K is 0.9 volts. This is 3.7. Again, relative to circuit ground, this is, let's do this in green. This is 0.3 volts relative to circuit ground times 4. This is 1.2 volts relative to circuit ground. 1.2 volts above 2.5. This is just a push amplifier, V plus equals V minus. This is also 3.7 volts relative to earth ground, because it's relative to earth ground. 3.7 volts at 8 ohms is 462 milliamps. This has a beta of 300. Depends on the transistor you're using. If I use one at the beta of 300, this is your current divided by 301, beta plus 1. And the op-amp's capable of 1.5 milliamps, not a problem. So 0.3 volts in, relative to earth ground, or relative to circuit ground works. When you're at circuit ground, if this is 2.5, that's 2.5. These are the same. The current is 0. This is 2.5. V plus equals V minus, 2.5, 312 milliamps divided by beta plus 1, 1.04 milliamps. Again, I can do it. It's capable of 1 milliamp. 602 is actually capable of 25 milliamps. And when you're 0.3 volts below circuit ground, so this is 2.5 minus 0.3. So minus 0.3 volts relative to circuit ground. This is also 2.2. Now I have 0.3 milliamps going up versus down in the first case. So this is also 0.3 milliamps. This is 0.9 volts, less than 2.2, 1.3. And 1.3 volts is minus 1.2 volts relative to circuit ground. So 0.3 in times 4 gives you minus 1.2. That's a non-inverting amplifier centered at 2.5 volts. 1.3 volts going to earth ground is 162 milliamps divided by beta plus 1, 0.5 milliamps. So that's what you should see. If you build it, you can then get some data. Or, correction, if I go in Circuit Lab, I could then simulate this. Again, when I simulate this, I'll have to have this biased by 2.5 volts. So, because again, circuit ground is 2.5 volts. If I go at 0 volts centered, this is going to be really negative, and V2 is going to saturate. So I need to have this have a DC term, 2.5 volts, plus an AC term, 0.3 volts. So this is V1 relative to earth ground. And here's 0 volts, earth ground. This is 2.5 volts relative to earth ground. 0.3 volt sine wave, giving you V2 amplified by 4, that then drives the speaker. And if you look at the output, here's what I see. Here is V1 plus or minus 0.3 volts relative to circuit ground, relative to 2.5 volts, amplified by 4. Which one's which? V2 and V4. That's these guys right here. No, right here. That's V2 and V4. Times 1.2, or times 4, gives you the output Y. And notice what the input is large, the output is large. Input is negative relative to the circuit ground. The output is 4 times more negative. Sine wave in gives you sine wave out. That's what you want. The base is up 0.7 volts. That's just I need a 0.7 volt drop across this guy, or whatever the voltage drop is across your transistor. Not that I really care, but it's there. So that's in Circuit Lab. In hardware then, you can build it and hopefully get the same result.
Okay, here's the push amplifier. Right here, I've got the microphone going through a capacitor to block the DC because I'm using my computer, and ground is earth ground, not floating. 2.5 volt reference that goes to this line. Here's my times 10 amplifier. I use times 10 just because it was too quiet. Amplify a little bit. It's actually times 11. Goes to the push amplifier. There's my power transistor and my speaker. So starting out, to measure these signals, I'll have a 600 Hertz square wave coming from online tone generator. This is the voltage of the input. That's RMS voltage. I go over to the output of the amplifier. .444 millivolts RMS, and then going to the push amplifier. Here's the voltage across the speaker. And my cable just came undone. So the push amplifier is working. Y equals X. That works best with a sine wave input. Once that works, you can switch over to an audio signal. And that's kind of what you're looking for. Fairly clean audio signal, Y equals X. So if I have a clean audio signal coming in on the right over here, that should be amplified and go directly to the speaker. And kind of notice that with audio, it's more fun to listen to, but it's really hard to measure because the voltage is bouncing all over the place. Depends on the audio signal. So that's the push amplifier.
Option 2. If you do have access to a plus-minus power supply, I could build a push-pull amplifier. The NPN is push, PNP is pull. In this case, doing the same thing, I want to find out what's the input when it's plus 0.3, 0, and minus 0.3 relative to circuit ground. In this case, circuit ground is earth ground. So at 0.3 volts times 4 gives you 1.2 volts. 1.2 volts makes the output 1.2 volts. 1.2 volts at 8 ohms is 150 milliamps. This has a gain of 1,000 if you use the TIP. So it's the 150 milliamps divided by beta plus 1. And the voltage here is your 1.2 plus whatever VBE is. If it's a Darlington pair, it's plus 1.4 volts, 2.6 volts. If it's a 6144, it's plus 0.7. If you're at 0 volts, then this is 0, 0 times 4 is 0, this is 0, this is 0. This actually is something between minus 0.7 and plus 0.7. Either way, I can't turn on the diodes, and the output is 0. So I don't really know what this is. Something between minus 0.7 and plus 0.7. At minus 0.3 volts, this is minus 1.2 volts. This is minus 1.2 volts. I now have 150 milliamps going up. The current goes this way. That turns on the PNP. Most of it goes down. A little bit goes left. That'll be this current divided by beta plus 1. And the NPN is turned off. In hardware, I can apply a sine wave in and measure the voltages. Again, sine waves are nice because I can take measurements with a sine wave. It's more fun with an audio signal, though. To simulate it, again, I'm going to use a sine wave as an input. Sine waves let you get some data. So let's use a 1 kilohertz sine wave at 0.3 volts peak. And here's what I see. Here's your Vn, that's X. Here's the output Y. Y is 4 times X. And this is the voltage at the base. So up here, I'm doing push. it's the output plus VBE. Over here I'm doing pull, the PNPs turn on. You can spell pull right, P-U-L-L, there we go, pull, is this voltage minus VBE. And when the output is 0, again, I'm somewhere on this line. I'm not really sure what the base voltage is. It's somewhere between minus VBE and plus VBE. Then hardware, we can give a demo.
Here's a couple examples of a push-pull amplifier. Now right here I've got the NPN and PNP. Currently just have a low frequency sine wave driving it directly. So as you go forward and back, you can see the crossover distortion, that little elbow right there. That convinces me that the push-pull is working. Next, here I had the op amp in the front set up as a voltage follower. Instead of having the V minus going to V out, I'm going to take V minus and have it go to the speaker, to the emitter. What that does is that eliminates the crossover distortion. And I got some noise on the signal. This is for a low frequency sine wave, and you can see the speaker going back and forth. Fairly smooth without the crossover distortion. And just for fun, this is the voltage at the base. And kind of there's that big jump. That's as I go from push to pull, I have to go from minus 1.4 volts to plus 1.4 volts. Okay, and once you're semi-convinced that the push-pull is working, I can increase the frequency, in this case to 400 Hertz. Kind of annoying. At 400 Hertz, I can measure the gain of the first stage, measure the gain of the push-pull from the input to the speaker. The input to the speaker should be a gain of 1, RMS. And then this guy should be a gain of 4. That's for sine wave input. Of course, the more fun input is to input a song. Makes it harder to take measurements, but it's a lot more fun to listen to. And ideally, you should have a fairly clean audio signal. What we'll be adding later is a filter that goes in here, goes between the preamp, filter, power amp, push-pull.